So with 4.1b, I'm going to start with example 2, bottom of page 323. And I have 3x minus 5y equals negative 2. 2x minus 3y equals 1. Okay, so one of the first things I do is I look and see if I were to add the x's or the y's together, do I get rid of the x's or the y's? I get 5x there, I get negative 8y there. So I want a 0y or a 0x. Don't get that with either one of these. So now I need to find out, can I make these two numbers the same? Can I multiply 2 by a number to get a 3 so that they're the same? Nope. Can I do the same with the 5? Can I get these two to be 5s? No, there's no number I can multiply by negative 3 to make that a 5. So when that's the case, sometimes you have to change both the numbers. So what numbers do I have that 3 and 2 both go into? Well, 2 goes into 4, but 3 doesn't. 3 goes into 6, and 2 goes into 6. So if I could make those 6s, where this one's a negative 6 and this one's a positive 6, then I can do that. So what would I have to multiply by this whole thing to make this into a 6? I'd have to multiply the whole thing by a 2. So let's do that over here on the right. 6x minus 10y equals negative 4. Don't forget to multiply by the end there, the other side of the equal sign. All right, so that's a 6. Now what does this have to be? Well, in order to add this to this and get 0, this has got to be a negative 6. So I'm going to multiply this whole thing by negative 3. And that gives me negative 6x, which is what I want, plus 9y equals negative 3. There. Now I can add these together, and those go away. I'm not going to cross those out, though. When I add my y's, I get a negative 1y. And when I add negative 4 and negative 3, I get negative 7. And if you remember right, if you want to, well, in fact, let's take out the 1. Let's just make it a negative. If you ever want your variable that's negative to be positive, you get it by itself, and you just change the signs of everything. I'm just going to write it as y equals a positive 7. Means the exact same thing. It's as if we're dividing both sides by negative 1. So there we go. There's our y value. Now to find our x value, we take either one of these equations or either one of these, stick the y in, and see what our x is. I prefer to take one of the original equations simply because it deals with smaller numbers than when you multiplied by 2 or negative 3 and makes bigger numbers. So I'm going to take 3x minus 5, and we found out that y is 7, so we're going to put a 7 there, equals negative 2. So 3x minus 35 equals negative 2. We're going to add 35 to both sides. 3x equals 33, so x equals 11. Okay, that looks good. So now my point of intersection, my answer, is at 11, 7. Okay, so let's go to example 3. So there's example 3. And again, we're going to look at this and see if there's anything we can come up with to get rid of either the x's or the y's. It doesn't matter which ones you get rid of. But I notice here I've got a 4 here and a 2. So if this turned into a negative 4, I could add negative 4 and positive 4 and get 0. So what do I have to multiply times this top to make that a negative 4? Multiply it by a negative 2. And I'm going to do this down below here. Negative 4x plus 6y equals negative 8. And this is going to stay the same. I don't have to multiply it by anything. Now I can add. And my x's go away. I have 11y, and negative 8 plus 3 is negative 5. divide by 11, and my y equals negative 5 over 11. That is not pretty at all, but it's what we get. So let's take that y and put it up into one of these problems up here. And again, doesn't matter which one. Let's go ahead and pick the top one just because it's there. 2x minus 3 times and this is where your skill at fractions comes in. So I multiplied 3 times 5 and got 15, both negatives, so now we have a plus. Okay, so now we need to subtract 15 over 11 from both sides. Okay, this is where it gets really fun. So 2x equals, I need a denominator of 11, so 44 over 11 for the 4 minus 15 over 11, which is what we have. 29 over 11. Oh, goodness. Okay. So now we have to divide by 2. And remember, when you divide by a fraction, we're going to call that 2 over 1. It's the same as inverting it and multiplying it. So turn it upside down and multiply, and we get 29 over 22. So my x value is 29 over 22, and my y value is my negative 5 over 11 that I got there. And that's the answer. Not real fun when you get these doggone fractions, but that's kind of what you're going to run into. You're going to get fractions. Okay, so let's keep moving here. I'm in example 4. I've got 5x minus 2y. You notice all these examples, there's always little tweaks that make it a little bit different. They don't just give you 14 different examples to show you the same way to solve these. They give you 14 examples or so because you're going to run into some struggles along the way. And this is one of those struggles. So in order to do this, I need either this 5 to be a 10 so that I can add these, or this 2 to be a 4 so I can add these. Does not matter which one. Let's just do the x here because it's there. So we're going to multiply this whole thing by 2. So that gives me 10x minus 4y equals 10. And the bottom will stay the same. Okay, let's add these. 10x plus negative, or 10x minus 10x goes away. We have nothing there. Negative 4y plus 4y gives me 0, nothing there. So I have 0 on this left-hand side, and these two add together to be 25. When you are doing these, and you end up with an answer with no variables, that is not a true statement. So like if I got 6 equals 6, I don't have any variables, but it's a true statement. This is not a true statement. That means that when I graph these, I'm going to get 2 parallel lines. There's no x and no y. They both went away. There's no x or y there. So all that means is that when you graph these, you're going to get 2 lines that do not cross. They're parallel. There is no solution. This ends up being your answer. Okay? So again, when your variables go away and the statement that you get is a comparison between 2 numbers, and that's not a true answer, that means your 2 lines are parallel. Okay, so far we've done lines that cross at one point, and we use the addition method in order to figure that out. Next one is if the lines do not cross at all, if they're parallel, So we figured out that. Now this one is the third one if the lines lie on top of each other, which the only way, whoops, let me get a different color. The only way they would lie on top of each other is if the equations were the same. Now they don't necessarily look the same, but they are the same because look what we've got here with our second equation. It's the same equation, whereas everything is multiplied by 2. Okay, so the 4 is doubled, the 3 is doubled, the 2 is doubled. So these are the same equations. They just look a little bit different. But let's say that you looked at those and you didn't know they were the same equation. Well, let's go ahead and solve and see what we come up with. Okay, I want this to be a negative 8. So that when I add this, I get 0. So let's multiply the whole top problem by negative 2. So I get negative 8x minus 6y equals negative 4. And if you notice, a lot of the same things are happening. Add those, add those, add those. You get 0, 0, 0. Okay? Which 0 is equal to 0. That's a true statement. And when you graph these, what you're going to get is you're going to get the red line and the blue line on top of each other. So that means that there are an infinite number of solutions here. Okay, so remember what I said a little bit ago about some of the examples being a little wacky so that you can get an idea of some of the things you can run into. Now, you can make these fractions the same. I mean, I can find a number that I can multiply by 1/4 to give me negative 1/2, so that when I add these, they go away. But when you're dealing with fractions, you're dealing with a bigger chance of error. So what I'm going to do is I'm going to multiply each of these equations by numbers to get rid of the fractions. So I've got a denominator of 2 and 3, so I'm going to multiply both of these by the greatest common, or the least common denominator, which in this case, if I make them, if I multiply them by 6, I get rid of my fractions. So 6 times 1/2 is 3. 6 times negative 1/3 is negative 2. 6 times 2 is 12. That looks a lot prettier. Okay, same thing here. I've got a 3 here and a 4 here, so I'm going to multiply by 12, since that's the common denominator. So 12 over 4 is 3. 12 times 2 is 24, divided by this 3 is going to be 8. And 12 times 6 is 72. That is a lot easier to deal with. Now, look what I've got here. I've got 2 of the same numbers here. Problem is, they're both positive, so when I add those, I'm going to get 6. If I want them to be 0, then this one or this one of them has to be a negative, right? Well, here's the cool part about this, as far as when you've got negatives like that, is I am going to put a negative here, and I can do that only if, come on, I can't get this to erase. There we go. Only if that changes to a negative and that changes to a negative. So as long as I change the signs of everything, then I'm good to go. Okay, so now I've got my line across here. These go away. This is negative 10y, and this is negative 60. So my y then is 6. Take this, plug it in here into the original one. X minus 12 equals 12. 3x equals 24. My x is 8. So my answer for this is 8 and 6. And I'm done. So the key thing in this particular example was get rid of the fractions. Okay, so that is 4.1b, and we'll go into 4.3 1c and talk about the substitution method.